Hidden behind every automated factory, conveyor system, and robotic arm is one core device that makes it all possible. It's not a robot, it's not a sensor. It's a PLC, a Programmable Logic Controller. Without it, modern automation wouldn't exist. But what exactly is a PLC? And why is it so important to everything from bottling plants to smart buildings? What tells a machine when to start or stop? What keeps a production line running in perfect sync, without human intervention? And how can one compact device control entire systems with millisecond precision? Do you want answers? Watch the full video to get them. What is a PLC? A PLC, or Programmable Logic Controller, is a specialized industrial computer used to control machines, systems, and processes with precision and reliability. At its core, a PLC is designed to do one thing exceptionally well: make decisions based on input conditions and execute actions instantly. Imagine a traditional control room filled with hundreds of relays, switches, timers, and wires, all doing basic logic operations. That was the old way. It was bulky, difficult to troubleshoot, and inflexible. PLCs replaced all of that with compact, software-driven logic, giving engineers the power to reprogram control sequences without rewiring hardware. That's a game changer. Instead of manually connecting electrical paths, you now write a digital program, often resembling electrical schematics, that tells the PLC what to do when certain conditions are met. Whether it's starting a motor, opening a valve, or redirecting a robotic arm, the PLC constantly reads signals from sensors, processes that logic, and sends commands to the appropriate devices, all within a fraction of a second. It's not just a controller, it's the real-time decision maker at the heart of industrial automation. Architecture of a PLC. To understand how a PLC works, you need to know what it's made of. The architecture of a PLC is built around a set of key components, each with a specific role in controlling machines and systems. At the foundation is the power supply. It doesn't just feed energy into the PLC, it ensures that power is stable and consistent, protecting the system from voltage fluctuations or electrical noise that could cause failures on the factory floor. Next comes the CPU, or Central Processing Unit. This is the brain of the PLC. It's where the logic lives. The CPU reads input signals, executes the control program, makes decisions based on conditions, and updates outputs accordingly. It handles everything from simple on-off commands to advanced control algorithms. Then there are the input modules. These connect the PLC to the outside world. They receive signals from buttons, sensors, switches, and other field devices. These signals tell the PLC what's happening in the environment, like whether a bottle has passed a sensor or if a motor is running. On the flip side, you have the output modules. These send commands from the PLC to actuators, motors, solenoids, valves, or even lights. They're responsible for turning decisions into action. For example, starting a conveyor or activating a robotic gripper. And finally, there's the programming interface. This is the link between engineers and the PLC. Through a laptop or HMI, human-machine interface, programmers write, test, and upload control logic to the CPU. They can also monitor the status of inputs and outputs in real time, making troubleshooting much easier than in traditional relay-based systems. All these components work together to make the PLC a powerful, flexible, and dependable solution for controlling industrial processes. How does a PLC work? So how does a PLC actually work? At the core of its operation is a continuous, lightning-fast cycle known as the scan cycle. This process repeats endlessly, often in just a few milliseconds, and it's what allows the PLC to respond to real-world conditions in real time. Here's what happens in each scan. First, the PLC performs an input scan. It reads the current status of all input devices connected to it, like sensors, switches, and buttons. It gathers all this information and stores it temporarily in memory. Next is the program execution phase. Based on the input data, the PLC runs the user-defined control logic. This could be something simple, like if sensor is triggered, start the motor, or something more complex involving timers, counters, and conditional branching. Then comes the output scan. The PLC updates all the output devices, turning on motors, opening valves, sending signals to actuators, based on the logic it just executed. And finally, there's housekeeping, where the PLC performs internal diagnostics and communication tasks, like updating system status, checking for faults, and preparing for the next scan. This entire process loops continuously, fast enough that the machine responds to changes in milliseconds. The result? Seamless, real-time control that keeps everything from bottling lines to elevator systems running smoothly and safely. It's this constant loop of sensing, deciding, and acting that makes PLCs so essential to industrial automation. Programming languages. PLCs aren't just about hardware. They're powerful because of how flexible and programmable they are. And that flexibility comes from the languages used to program them. There are several standardized languages defined under IEC 61131-3, and each one is suited for different kinds of tasks and user expertise. The most common is the ladder diagram, LD. This language looks like an electrical relay circuit diagram, which makes it especially popular among electricians and technicians coming from traditional control systems. It uses symbols like contacts, coils, timers, and counters, so logic flows visually from left to right, like an electric current. It's great for simple on-off logic and widely used in manufacturing. Next is structured text, ST. This one looks more like a traditional programming language, similar to Pascal or C. It's fully text-based and ideal for more advanced control scenarios like complex calculations, nested logic, and handling large data sets. Engineers with a software background often prefer this language for its precision and readability. Then there's the function block diagram, FBD. This is a graphical language that uses visual blocks to represent different operations or functions like AND or logic, timers, counters, or PID controllers. Blocks are connected with lines that represent the flow of data. It's intuitive for engineers who work with process control or who think in terms of modular systems. Other languages like instruction list, IL, and sequential function chart, SFC, exist too, though they are less commonly used today. The beauty of modern PLC platforms is that they often let you mix and match these languages within the same project. So you can use ladder for basic machine control, structured text for math-heavy operations, and function blocks for system-level logic. This level of flexibility makes PLCs incredibly powerful and adaptable to just about any industrial challenge. Applications of PLCs. PLCs are everywhere. Once you understand how they work, you start to realize just how many industries rely on them to keep critical systems running. In manufacturing, PLCs are the backbone of production lines. They control machines that fill bottles, weld car parts, sort packages, and assemble products. Every movement, every timed sequence, and every sensor input is managed by a PLC working behind the scenes. In building automation, PLCs are used to control lighting, elevators, HVAC systems, and security setups. They can monitor room temperatures, detect motion, and adjust systems automatically for energy efficiency and comfort, without human input. In transportation, they control traffic lights, railway signals, and even safety gates. When a train approaches a crossing, the sequence of flashing lights, barriers lowering, and alerts triggering. It's all handled by a PLC. They're also widely used in energy plants, water treatment facilities, logistics centers, agriculture, and even theme parks. Basically anywhere you need reliable, real-time control over machines or processes. What makes PLCs so valuable is that they don't just perform one task, they adapt. With the right program, one PLC can control a robotic welding station today and a packaging line tomorrow. That's why they're considered the unseen heroes of automation, quietly powering the world around us. PLCs offer several key benefits that make them essential in modern automation. Reliability. They're built to withstand harsh industrial environments, heat, dust, vibration, and electrical noise. Flexibility. Reprogramming a PLC is simple. Need to change the logic? Update the code. No rewiring needed. Scalability. Whether you're controlling a single motor or an entire factory, PLCs can scale to fit any size system. Take a basic packaging line. A sensor detects when a product reaches the packing station. The PLC receives that signal and immediately activates a robotic arm. The arm picks and packs the product, exactly on time, every time. It's a simple example, but it shows how inputs, logic, and outputs come together to automate real-world tasks. PLCs are the brains behind modern automation. They control machines, manage processes, and ensure that systems run smoothly, day and night, without fail. Understanding how they work isn't just useful, it's essential for anyone in engineering, manufacturing, or industrial tech. If you found this guide helpful, hit that like button, subscribe for more content on automation, and drop a comment if you have questions. Want to go deeper into industrial systems? Stick around, this is just the beginning. This video is produced by Autom8, the platform connecting robot and PLC programmers with companies building the future of automation. Visit autom8deal.com and stay ahead in the world of smart manufacturing.